Hello, we're going to continue talking about cams today. So last time we did an introduction to cams, some terminology, a little bit about SVAJ diagrams. Today we're going to talk a little more about the functions to use for critical extreme position cams. Specifically we'll talk about how to take a cam program like rise dwell, fall dwell, which is something like an automotive cam shaft might have something like that. And it's probably going to be more, if we look at these, let me get my pen here. For the intake it would be dwell, rise, dwell, fall, dwell. So we take that program, we take our timing, and then we want to connect the dots and actually make these nice curves here that behave on our SVAJ diagrams. So we need a timing diagram. That's our first place to start. So our timing diagram, so the x-axis is the angle of usually the crank in a machine, but it could be the angle for the cam itself, but for an engine it's going to be the angle of the crank. So it'll be 720 degrees for a 4-stroke engine, 360 degrees for a 2-stroke engine. And then this is going to be rise of the follower. So here there's no rise to the follower. Here there's, the maximum rise to the follower here, like 1 inch, 1 millimeter, whatever our units are. So for this cam, we want it to be at 0 height, so on the base circle radius for 90 degrees. We want it to rise for 90 degrees. We want it to be fully at the maximum amount of rise for 90 degrees, and then we want it to fall back down to the 0 position at over 90 degrees. So it's going to be 90 degrees of dwell, 90 degrees of opening, 90 degrees of dwell, 90 degrees of closing, and then repeat. And we want to connect the dots with this. So whatever functions we use to connect the dots with, we need it to meet those rules we talked about last time, where position, velocity, acceleration are continuous and jerks finite. So if we just connect the dots with straight lines, the position's actually continuous, right? Well, what's going to happen with velocity, though, when I draw the velocity diagram, so from here to here, velocity is going to be 0. Here, velocity is the slope of this, so there's going to be something like this. It's going to be discontinuous, right? Here, the velocity is going to be 0, and then here, the velocity is going to be negative. So this would be our origin here. And so you can see immediately that the velocity is discontinuous. And so when you draw acceleration is going to be 0, because the slope of that line is 0, and then velocity gets from here to here, and it does that by having a little infinite spike up, but then it's 0, and then there is an infinite spike down, it's 0, there's another infinite spike down, it's 0, and then there's an infinite spike up. These infinite spikes of acceleration, so if you think about that, the velocity changes from nothing to something in an instant. And the only way a velocity changes from nothing to something in an instant is an infinite amount of acceleration in a short period of time. Very short period of time, infinitely small amount of time. It's like an impact. So what's going to happen, the cam is going to be following around this thing, and it's essentially, when it gets to these changes, it's going to be like an impact. And that's going to cause all sorts of wear and damage and vibration and noise. It's just not good. So this is fun. This just doesn't work. Now, when I add some base circle radius to this thing and wrap it around in a circle, it actually doesn't look terrible. It doesn't look like all straight lines and notches like this when I wrap it around a circle. So, it'd be hard to tell looking at the actual metal of the cam lobe whether it's bad or good or not. You have to really look at these SVAJ functions. That's something we'll talk more about in the next cams lecture, is how to actually add a base circle radius and wrap it in a circle to make a cam lobe, the actual metal that you'd grind. So I've got the V graph here, but the acceleration graph would be 0, 0, infinite up, 0, 0, infinite down, 0, 0, 0, infinite down, 0, 0, infinite up. And it's bad. Velocity is discontinuous, which right away that breaks it. So it's not a good design. So we want We want something better. Now, those infinite spikes of acceleration are called Dirac delta functions. You can actually mathematically model their effect. That's something that you'll talk about in controls. You'll talk more about how to model Dirac delta functions. So, but again, we want to avoid those. So we don't want those in our system. So we need better functions. So again, to meet the fundamental law of CAM design, we need position, velocity, acceleration to be continuous. We need jerk to be finite. We need functions that work for that. So, types of functions. There is a sinusoidal, also called simple harmonic motion. It only works for rise-fall programs. When we put a dwell before the rise or after the rise or after the fall, if I put a dwell anywhere in there, it's going to break. So we can't do dwells, which makes it not very useful in CAMs. You know, if we don't need dwells, we really shouldn't be using CAMs. There's usually a lot better ways to get something to open and close if we don't need dwells. I mean, we can use a 4-bar for that, like we talked about way back in 4-bar synthesis, and we don't need to grind a CAM. We can make something out of just a bunch of simple links and revolute joints. But we'll go ahead and go through the equations for this. So our position is going to be a cosine function. It's going to the rise event is going to last beta degrees. This is something that confuses people in this. Beta is a constant. Beta is the duration of the rise event. So beta is a constant. Theta is going to vary from 0 to beta. So theta is going to be from 0 to beta. Beta is a constant. H is the height of this. It's a constant as well. So essentially what this equation gives us is the shape of a sine wave that goes from 0 here to h here over the duration of beta degrees or radians, or either way. And this, you can see that these divide out, so either sets of units work because of this pi in here. So the cosine function we're going to do in radians, the theta over beta gets rid of units, and then it will be from 0 to pi radians. Take the derivative of this equation, you get this. It's easy to prove. Note that the beta comes out of this thing. So right here, this can't be in degrees. So here it's fine if beta and theta are both in degrees. Here it's not fine. So when in doubt, use radians. Radians will make this safe. If your graphs look really weird sometimes, when you're trying to plot SVAJ diagrams, chances are you probably did beta in degrees, and you get divided by 360, divided by 360 squared, divided by 360 cubed, and it really screws up your results. So make sure, at least for this part of it, you're in radians. Over here you can be in degrees, but for here you definitely, that beta's got to be in radians, or you can just do the whole thing in radians and life works better. Take the derivative of again, I get acceleration, derivative again, I get jerk. And when I plot these things, so I plotted these before. You know, this plot here is these equations with no dwell. Now, when I put dwell into this thing, this is where it's going to break. So how I use this, so this theta, it's kind of a little hard to explain, but these equations are valid during the rise event. They're valid when I go from the height of s equals 0. Stop doing that, to s equal h. That is when this equation's valid. It's not valid from here all the way over to here. You don't just use one equation for this whole graph. You have to do this piecewise. So from the initial dwell here for 90 degrees, I hard code in zeros for everything in my spreadsheet. Then from 90 to 180 degrees, that's the rise event, and these equations are valid. So for this, I need the duration of the rise event. That's 90 degrees. So the duration of this is beta, and in this case, it's 90 degrees. The theta that I plug into this is not this axis here. It's not this theta here. The theta that we plug into this equation starts at 0 and goes up to beta here. So theta is going to vary from 0 degrees, 1 degrees, 2 degrees, 3 degrees, up to beta for here. So I really need to keep track of two angles when I do this in a spreadsheet. The angle for just the rise function, and then the angle for the actual plot. Because this is going to go 0 90, 180, 270, but the theta I actually plug into this equation needs to go from 0 to beta here. So I actually keep track of those two things separately when I try to make a spreadsheet with this. So plug in theta equals 0 to 90 degrees here with an h of h is 1 in this case, with h equal to 1, and these equations will give me all of these curves here. So now I need to hard code in the dwell that happens after the rise. So for that dwell, S is equal to H, and then V is equal to A is equal to J is equal to 0 for this portion. So I hard code all of that in. Again, these equations are not valid. They're only valid for the rise. They're not valid for the dwells. They're not even valid for the fall. You have to modify them a bit for the fall. So from here on, I need to do the equations for the fall of this thing. And if you'll note, they're not just these things symmetric. They're not just these things run from theta equal 90 degrees down to 0. There's some minus signs involved, and I'll talk about how to apply that in a later slide. But the main thing to get is that these equations are only valid for the rise part of your CAM program. And everything else, all the dwells you have to put in and all the falls, you have to modify these equations a little bit to be able to use them. So that's the important thing to get. H and beta are constants. Theta varies between 0 and beta. Anything before or after I have to add on manually. And I have to put a couple minus signs in here whenever I do the fall, and I'll tell you how to do that in a second. Main thing to note here is this discontinuity in acceleration. Acceleration is 0. Bang, there's acceleration. Acceleration is negative something, bang, it's 0. So acceleration is not continuous, therefore there's really going to be some infinite spikes of jerk here, and then here, and then there, and there. There's going to be infinite spikes of jerk that are going to cause problems. So this doesn't work. This sinusoidal or simple harmonic motion doesn't meet the fundamental law of CAM design. So to fix that, we're going to use cycloidal. We're still going to use sine and cosine functions, but we're going to fix the problem at the acceleration and make sure it works for the other ones. So we're going to define our generic equation that we're going to use to model the rise. So we're just going to use c times, use the sine function, 2 pi theta over beta. That's the generating function we're going to use for acceleration. So acceleration is c times sine 2 pi theta over beta. All right, acceleration is dv dt, right? I can move dt over here, separate variables, integrate both sides, and I get on the left side velocity, on the right side I get this integral here that I can evaluate. Now it's implicit, so I need a constant of integration here, so I'm going to need to apply a boundary condition. My boundary condition is when theta is equal to 0, I need velocity to be continuous. So if I have a dwell, velocity 0, then as soon as I get into the rise here, I need the velocity to start at 0. So that's my boundary condition that ensures that at the start of the rise, velocity is continuous. That allows me to solve for my constant, and I get K1. So plug in V is 0, theta is 0 into this equation, and it simplifies down to this, and I can solve for that constant K1. So go ahead and plug that in. I can factor out here, I get this beta over 2 pi that I can pull out of this thing and simplify it a little bit. Now I need to get to position. So velocity is ds dt, right? That's the definition of velocity, is its derivative of position with respect to time. Separate variables and integrate again. Left-hand side is position, right-hand side, I need to evaluate this integral. Again, that's not a terribly bad integral to evaluate, but it is implicit, so I don't have limits, so I have a constant of integration K2. Just like with velocity, I use a boundary condition of I want position to be continuous, so at the start of the rise function, where theta is equal to 0, I want the position to be 0 as well, and plug in 0 in for theta, 0 in for s, and it simplifies out, and I get K2 equal to 0, which is great. So I have my s equation. Now, I haven't solved for c yet. So I'm going to solve for C. So my boundary condition I'm going to use for that is when theta is equal to beta. So when I rise and get to the peak lift here, I want this peak lift to be h. So when s is equal to h, so s is just this generic variable for the height, h is the maximum height. H is a constant, s is a variable. So when s is equal to h, when I'm over here, I want the height, when theta is equal to beta. So when I am over here at this constant beta, when theta is over here, I want s to be equal to h. So plug that in. So plug h in here and then plug beta in for theta. Note that I get 1 here, so I get sine of 2 pi. So I lose this whole term here, and I get c equal to 2 pi h over beta squared. So go and plug that back into all three of those equations, and I get equations for acceleration, velocity, and position. I need jerk. I need to take the derivative of this equation with respect to time to get jerk. So let's do that derivative. It's not bad. I get an equation for jerk. Summarizing those four equations, I have a equation for position, velocity, acceleration, and jerk. Apologize for the order. I should have rearranged this with first, second, third, fourth. But those are the cycloidal family of cam functions. So this gives me the SVAJ diagram for the rise, and only the rise, for a cam. Now, beta is a constant. That's the duration of the rise event in radians. You could do degrees in here again because it's theta over beta, but these betas out here have to be in radians. So that's beta is the duration of the rise event in whatever your units of angle are. Probably should use radians. Theta is going to vary from 0 to beta. H is the peak lift. It's a constant. So my independent variable is theta. My dependent variables are A, V, S, and J. And then I can plot those. Now, this looks a little bit different than the simple harmonic motion. You see position is nice and continuous. Dang, position is nice and continuous. Velocity is the blue one. It's nice and continuous. Acceleration, well, that was the one that was a problem for simple harmonic motion. It's nice and continuous. Jerk is discontinuous, but it doesn't have infinite spikes. So all I need is position, velocity, and acceleration to be continuous. Jerk can be discontinuous. It just needs to not have any infinite spikes. Now, the derivative of jerk will have an infinite spike in it, but we don't care about it in general for cams. So this would work. Downsides of the cycloidal cam is if we look at the acceleration plot here, it takes us a while to build up to peak acceleration, and then we're only at peak acceleration for an instant. So then we ramp down here, and we're only at peak acceleration down here. So we really would probably like to have a broader acceleration and smoothly ramp up to that, smoothly transition here, have a broader acceleration here, and then ramp up here. And we'd have a lower peak acceleration, and so we'd have a lower peak force, and it's just going to be, we can get the same thing done, get it done smoothly, but with lower peak force, and so less stress on the mechanism. So that's what when we start talking about other cam functions, we'll get into some that broaden that peak acceleration out in a bit. So the acceleration can be peaky, so we can do a little bit better than this. All right, now I need to show you how to model. So these equations are only valid from here to here. Again, this is all hand-coded in. This is all hand-coded in. This we haven't talked about. So how do I modify these equations for the fall? So what I need to do here, so I need to start here where s is equal to h, and then work backwards to where s is equal to 0. And so I need to run this backwards. So instead of going from 0 to beta, I'm going to run from beta down to 0. Now if I did that, these would literally just be mirror images of these curves. Here's the weird part. So when I originally derived these equations, I had theta increasing from 0 to beta, and time as time moved on in positive direction. So as I went into the future, theta went from 0 up to beta. The problem is if I try to run these equations backwards from beta down to 0, is now time is going forward, but beta is dropping. And all these dt's in these equations have the wrong sign on them now. So S doesn't have any dt in it, so it actually works. S is just purely mirrored. So here, this equation is, or this curve is this equation from 0 to beta. This is this same equation from beta down to 0, and it works perfectly fine because there's no dt in it. Velocity, which is ds dt, again, I'm taking those equations that I originally had where I went from 0 to beta, where time was increasing. I'm going down from beta down to 0, but time is still increasing. And so I need to flip the sign of the dt to get this to work out, because I'm counting down. I can't just change one thing without changing the other thing. I can't just count the angle backwards without counting the time backwards. So I put a minus sign in here for the dt, and this works. So the velocity, if you'll note, the velocity in blue, it's this run backwards but flipped about the x-axis. And if you look at the derivative of the slope of this curve here, you'll see that this works, because here the slope is negative. Stop doing that. Here the slope is negative, and it starts out, it gets negative, it gets negative, it gets negative, and it goes back to 0. If I just mirrored this, then the slope would be positive, and it doesn't work. For acceleration, I've got dt squared, so it doesn't matter if it's positive or negative. So the acceleration curve is just simply the mirror. It's beta down to 0. So here's the acceleration curve. Here it's just that mirrored. That time thing doesn't matter because the dt is squared. So there's no minus sign in this equation. For a jerk, I get dt cubed. So minus dt cubed is minus dt. All right, so the minus sign comes out of this thing, right? So I need the minus sign in this equation. So the jerk is run backwards, so run from here backwards to here, and then flipped about the x-axis. So essentially all I need to do to reverse any set of cam functions that were derived this way is, on the fall, go from beta down to 0 for your angle, and then put a minus sign in front of velocity and jerk. That's all I need to do, and I can reverse any cam profile that was derived, from 0 to beta with time going forward using derivatives. So it's easy to do. There's a little trick to it. If you do it wrong, your curves, your slopes won't make sense on your curves when you do your derivatives. So that's actually how I originally figured out how to do this. If you read the book, you'll see that this actually isn't in the book. The book doesn't talk about this at all. When I first did these slides, I ran beta down to 0 and didn't count for the time thing, and the slopes all looked wrong, and a student pointed it out in class, and I looked at it and was like, you know what, that's really wrong. And I had to actually go through and figure out why you couldn't just run beta down to 0 like this, and I figured out this dt thing, and it works. It works great. So this is not something you'll find in the book. So to reverse these, you need a minus sign in velocity, you need a minus sign in jerk, you need to count beta down to 0. Okay, so let's do a better job. So let's say we do constant acceleration. So now our acceleration is going to be no acceleration, no acceleration, no acceleration, bang, constant acceleration, bang, constant acceleration, and then back to 0. Acceleration is not continuous, right? So that's not going to work. But let's say I interpolate up to it, right? Like something like that. Now that acceleration is continuous, right? This is a continuous function. Now jerk will be discontinuous, but acceleration is continuous, which is all I need. So that meets the fundamental law of cam design. That's trapezoidal acceleration. So jerk is finite, but there's discontinuities in jerk. So it can cause some vibrations, but it works pretty well. But I can do even better. I can use a little bit of a sine function to smooth this out, and I can make it even better. Right? So that's mod trap. Mod trap is really good. It has a lot of constant acceleration, and I use a nice smooth function to interpolate, which is based on the sine family of functions. This is just a stretched out sine wave here. Mod trap is really good. It's well behaved. Our peak acceleration, since this is broader here, the acceleration is even better. So it's good. Mod trap is, I mean, honestly, for most problems, you might as well just use mod trap, because there's other functions that are good, but it's hard to beat mod trap for most situations. So again, there's not a lot of downsides in modified trapezoid. So how do I model this? This is even more piecewise than before, because now my rise function's got all sorts of different zones. If you look at this, there's going to be 1, 2, 3, 4, 5 zones right here, just in the rise part of it. And if I add dwells before and after, I have more zones, and it gets real piecewise. And so I really want a piecewise derived set of equations for modeling this. And maybe I want to model all sorts of other stuff and don't want to rederive equations from scratch. So that's where SCCA comes in. SCCA is a family of functions that are built up piecewise that let us model all sorts of different cam profiles, from constant acceleration to simple harmonic motion to modified trapezoid, modified sine, and cycloidal. Mod sine we haven't talked about. All mod sine is when I go back to sinusoidal, when I go back to here, all mod sine does is it squishes this thing down like this and introduces a little sinusoidal ramp at the start, and then there's a little sinusoidal ramp at the end of this that fixes the simple harmonic motion. I don't know why you'd want to do that when you've got mod trap, but we can model it. So these equations will let us model all of these things in one set of equations. This is really cool. So we're going to need some normalized variables for this. So normalized variable x, that's our x-axis, it's going to be theta over beta. So instead of going from 0 to beta on our angle, we're going to go from 0 to 1. The output, instead of going from the height s equals 0 to the s equals the peak height h, we're going to go from 0 to 1. So we're going to normalize the position. So x is normalized cam angle, y is normalized follower height, theta is still our cam angle, beta is still a constant, which is the max, the duration of the rise event in degrees or radians. S is our instantaneous follower height, h is the max. So constant, constant, normalized, and normalized. All right, zones. The first zone here, so that is going to be that transition zone. So from 0 to this constant b over 2, b is a constant, we'll talk about it in a second. So for 0 to b over 2 for b not equal to 0. In this, our position, our normalized position, takes this form. And I'm not going to go through and derive this, it's a mess. But it's already been done for us, and it works for all these things. Y prime, that's our normalized velocity. We just take the derivative of this. Y double prime, you'll see it is this sine function here. So y, this is really what's driving this all. And in this portion of the acceleration, this is our sinusoidal ramp up. Like at the start of mod trap, that sinusoidal ramp up to constant acceleration, that's really what this is. And then this is just the integral, this is the integral with the constants of integration thrown in there. Jerk, we take the derivative of that and we get our jerk. The second phase, this is our constant acceleration phase. So here our acceleration is a constant, and we'll talk about what CA is, but that's our constant acceleration. So here in that first zone, our acceleration looked like this. Here our acceleration is constant. So we take our integrals here with our boundaries conditions to get these equations for the normalized velocity, normalized position. Take the derivative of this, it's going to be 0, right? The jerk would be 0 in this phase. Now in this phase here, so for the acceleration it was going to be this constant. Here we need this sinusoidal ramp like this, so the acceleration is going to look sinusoidal. So when I look at the acceleration, actually it's a cosine function, but then to integrate it and get the boundary conditions to line up, it starts to get a little messy for normalized velocity, and then it gets real messy here for normalized position. And then jerk is just going to be another, cosine becomes sine with some constants, not a big change. Zone 4, this is going to be a constant acceleration zone, so you'll see the here in zone 4 the acceleration is the negative of that same constant it was when it was over here in zone 2. Plus when I integrate this thing, I got to get all these limit boundaries to work out, so it gets a little gory up at the position. Jerk's going to be 0 though. Now to smooth this thing off at the end, I need to go from here, smooth it back down to 0. So zone 5 is just going to be a little sinusoidal function to smoothly get this thing down to 0. And then the velocity and acceleration, sorry, velocity and position get a little bad because of the constants of integration and boundary conditions. Jerk will be pretty simple. Zone 6 is when I'm out here past the end of the rise function. Here the normalized position is just 1, and then all the derivatives are 0. Converting parameters, that constant ends up being a combination of these B and D parameters, which I'll talk about what their values are in a second. So I can find that peak acceleration factor. I can change the normalized position y to the actual position by multiplying it by the height. I can change the normalized velocity y prime to the true velocity by multiplying it by h over beta in radians. Acceleration, h over beta squared times normalized acceleration gives us acceleration. Normalized jerk times h over beta cubed gives me the actual jerk. So I do this piecewise. I start in zone 1. I write the equations for y prime, y prime prime, y prime prime prime. Then use the equation for CA and these to get them into the true position, velocity, acceleration, and jerk. Repeat that for all zones, and I can build a spreadsheet that lets me model pretty well any cam profile I want. So all I have to do to get the different kinds of cam profiles is get rid of some of these zones. So that's really what these B, C, and D parameters are. It's the width of the different zones. So for constant acceleration, there's no transition area, so I get rid of the transition area. And all of the cam profile is just constant acceleration. For mod trap, I have some of my profile is constant acceleration, and then I have some of it that are those sinusoidal transitions. For simple harmonic motion, I have no initial transition, no constant acceleration, and my shape's all what that final transition zone would be, where the acceleration would look like that. Mod sine, I have 0.25 for the initial sinusoidal, and then 0.75 is the other sinusoidal. So there's no constant acceleration, but I blend between the initial ramp up and then this final ramp up here. And then cycloidal is a mix of the initial and then the final transition with it doesn't have any constant acceleration in there. The beautiful thing about this is that I can blend between these things. So let's say, I start with mod trap, but for some reason I want to make it look a little more sinusoidal, have a little bit smoother transitions. I can blend between, so see, this is 0.5, this is 0.25, so I can lower this and increase this, and it starts to look a little bit more like modified sine. And by changing these parameters, I can make something it's a hybrid of these different functions. The only constraint on this, these all have to be positive, and they have to sum to 1. B, C, and D have to sum to 1, which essentially means pick B and D, and then 1 minus B and D is equal to C. So I really can only change 2 of these things because they have to sum up to 1. What you'll find when you plot these things is in position land, these don't look very different. This is the S-curve for these 5 different things using the different values of B, C, and D. They don't look very different, which means when I put a base circle on this and wrap it in a circle to make a cam lobe out of metal, they don't look different. But the acceleration looks really different. So constant acceleration, the acceleration is like bang, bang, bang. It's really, really bang, bang, constant back and forth. Mod trap, the acceleration is sinusoidal with a constant acceleration area with a little sinusoidal interpolation. Simple harmonic motion, the acceleration starts up here and then goes down. Mod sine, it goes up and then it goes down. Cycloidal is where it looks something like that. It's just a pure sine wave. So the accelerations look drastically different for these. The positions don't. Right? You can't just look at a cam usually. I mean, you can usually look at a cam and tell if it's bad, if it's just got like right angles and stuff in it and hard at corners. But, for something that's halfway decent, you can't just look at it and tell what these are. You'd have to actually measure the height in different places and plot it and then do the derivatives, which is a really noisy process. So it's really hard to actually reverse engineer a cam because the position doesn't change very much for these functions. I mean, this is really the maximum difference between simple harmonic and cycloidal. It's just there's not a lot of variation in there, right? You know, you might be talking just a few % change in the position. So you'd have to measure this very, very accurately. So that's it for cam functions. What we're going to talk about next time is once I have this curve, how do I turn that into a piece of metal that's an actual cam lobe? So that's pretty fun stuff too. So that's it for today, and I'll see you all next time.